Hello friends, this is Praveen Pawar. In this video, we are going to discuss the question paper of GATE 2018 for subject Electronics and Communication Engineering branch. Here we will see the questions from communication subject. So here we will start. First question is, consider the following in amplitude modulated signal. So here amplitude modulated signal is given. The ratio of the power of the message signal to the power of the carrier signal is. So first I'd like to give a brief introduction of amplitude modulation. Consider C of t carrier signal as AC cos omega c t. Here I am not writing the phase term because in AM only amplitude is of concern. Now message signal we can consider it as AM cos omega m into t. So here we can write the AM signal, which is given as AC plus m of t cos omega c t. Amplitude modulation is nothing but the amplitude of the carrier signal is varied in accordance with the message signal, while phase and frequency be constant. So here applying simple trigonometric rule, if m of t is equal to am cos omega mt, this expression we can expand it here as AC cos omega ct plus this would be am by 2 cos omega c plus omega m into t plus am by 2 cos omega c minus omega m into t. So here we observe that this is our carrier signal, this is upper sideband and this one is lower sideband. This AM modulated signal we will compare it with the given amplitude modulated signal in the question. So here we observe that this term represent to carrier signal, in which this 4 is our AC amplitude of the carrier wave, and omega c is equal to 2400 pi. This gives us a lower sideband and this term will give us upper sideband. Now we will calculate the power. So power of the message signal means the power of the lower sideband. Directly we can calculate it as the amplitude, the square of the amplitude divided by 2. So for lower sideband it would be 1 over 2, and similarly for upper sideband it would be 1 square by 2 is 1 over 2, and we have to calculate the ratio. So it will divide it by power of the carrier signal. So amplitude of the carrier signal is given as 4, so this would be 4 square and divided by 2. So on solving this, easily we will get 1 over 8, which is equal to 0.125. So our correct option would be, answer would be 0.125. Now question number 2. Consider a binary channel code in which each code word has a fixed length of 5 bits. The Hamming distance between any pair of distinct code words in this code is at least 2. The maximum number of code words such a code can contain is. So first I will tell you Hamming distance. Consider a code word is 1011 and another code word is 1110. So here you will observe that there are the change in 2 bits. So we will say that there is a Hamming distance of 2. Now come to the question. It is asking that binary channel code in which each code word has a fixed length of 5 bits. So there are total maximum possible code words are 2 to the power 5, means this total possible code words, maximum code words are 32, and out of 32 maximum number of code words which will give the Hamming distance of 2 would be just divided by 2, so it would be 16 here. So our correct option is 16. We can also verify it as by taking some example. Consider there is only 2 bits of code word, and having distance of 2 will give you another code word is 1 1. So this is 2-bit code word. Maximum possible code words are 2 to the power 2, that is 4. Out of 4 there are only 2 pairs which will give the Hamming distance of 2 also. So similarly we can say if there are total 32 code words, and out of which there would be 16 code words which will give the Hamming distance of 2. Now question number 3. A binary source generates symbols x belongs to -1 to 1 which are transmitted over a noisy channel. The probability of transmitting x is equal to 1 is 0.5. Input to the threshold detector is r is equal to x plus n. The probability density function fn of n of the noise and shown below. So here PDF is given. If the detection threshold is 0, then the probability of error is. Now first I will draw the PDF of our received symbol vector. So this is r, and the function is given as f of r. So here two symbols -1 and 1. We'll see that this is added with the noise. So we'll draw the PDF for x is equal to -1. So it will be here from -1, its amplitude would be 0.5, and width is from -2 to 2. So here it would be -3 to 1. Now this is for symbol x is equal to -1. Now similarly for symbol x is equal to 1, we'll draw at 1. We will start from -1 to 3. This is for as x is equal to 1. Here we'll observe that this overlapped area will give us the probability of received symbol. Probability of received symbol is 1 when s of 1 is transmitted. And similarly this overlapped area will gives us the probability of received symbol of 1 when s -1 is transmitted. Now we'll calculate the probability of error. The probability of error is given as the probability of symbol when s -1 is transmitted, and the probability of received symbol of 1 is detected when -1 is transmitted, which is plus probability of symbol 1 is transmitted is multiplied with the probability of received is -1, and when 1 is transmitted plus 1 is transmitted. So on putting the values, the probability of s -1, this the probability of transmitting x is equal to 1 is given 0.5, means probability of s1 is given 0.5. So remaining probability would be given for another symbol which is 0.5, which is equal to s -1. So here this is 0.5 multiplied by r1 on s -1 is given by the area of this triangle. This is the right angle triangle. Its area is given as 1 over 2 into 1 into the half of 0.5 is 1 over 4. So this is 1 by 8. Similarly, probability of s1 is 0.5, and this area is also is equal to 1 over 2 into 1 into 1 over 4. So this would be 1 over 8. So here we can write it as 1 over 8, which is equal to 0.125. So our correct answer would be 0.125. Now here is the next question. Let C of t is equal to AEC cos 2 pi fct and m of t is equal to cos 2 pi fm of t. It is given that fc is very greater than 5 fm. The signal C of t plus m of t is applied to the input of a nonlinear device whose output v naught of t is related to the output vi of t, as v naught of t is equal to a vi of t plus b vi square of t, where a and b are positive constants. The output of the nonlinear device is passed through an ideal band-pass filter with center frequency Fc and bandwidth 3 FM to produce an amplitude modulated wave. If it is desired to have the sideband power of the AM wave to be half of the carrier power, then A upon B is. So here, first the signal C of t plus M of t is applied to the input of nonlinear device. So here input is Vi of t is C of t plus M of t. So this we'll write it as AC cos 2 pi Fc of t plus cos 2 pi Fm of t, right? Fmt. Now it's given that the output win of t is related to S. So here we will write V output win of t is nothing but this is M of t. A Vi of t. A will be multiplied by this term Vi of t, so it would be AC cos 2 pi Fct plus cos 2 pi Fm of t. So this is first term, and second term is b Vi square of t plus b. So here we'll multiply these two terms. It would be AC square, square of these two terms. So a plus b whole square would be a square, means AC square cos square 2 pi Fct plus cos square 2 pi Fmt plus 2 AC cos 2 pi Fct into cos 2 pi Fmt, right? Now this output is passed through an ideal band pass filter with center frequency Fc and bandwidth 3 FM. So if we draw the characteristic of a band pass filter, so it is given that there is a center frequency Fc and bandwidth is 3 FM. It means this output terms only that terms will be passed which has the frequency Fc plus minus 1.5 FM, right? So here the output of this band pass filter Vb of t would be this term AAC cos 2 pi Fc of t would be passed through this. Sorry, this is cos 2 pi Fc of t will pass through this. This term cos 2 pi Fm of t will not pass because does not have term Fc, and which is out of this band pass filter. So this will not pass. Another term be AC square cos square 2 pi Fct. So this cos square 2 pi Fct we can write it as we know the cos square theta is equal to 1 plus cos 2 theta. So that term would be cos 4 pi Fct, which would be out of band. So this will also not pass through this band pass filter. Fc is not in this term, so it will also not pass. Here this term 2 AC cos 2 pi Fct into cos 2 pi Fm of t. If we apply the simple trigonometric property, so we'll observe that it would be cos A into cos B, it will be 1 by 2 cos A plus B plus cos A minus B. So Fc plus Fm This will pass through this, and Fc minus Fm will also pass through this. So by applying this, so these two will be cancelled out, and we will get B A C cos 2 pi Fc plus Fm of t plus BAC cos 2 pi Fc minus Fm of t. This is the output of the band pass filter. Now, if it is desired to have the sideband power of the AM wave to be half of the carrier power, so these two terms gives the upper sideband and lower sideband, and this term gives the carrier power, carrier signal. So while calculating the power, the sideband power is calculated as amplitude square divided by 2, so it would be b square AC square divided by 2 plus, for this upper sideband, and for lower sideband it would be b square AC square divided by 2. This term would be divided by carrier power, so it would be a square AC square divided by 2. So it is given that this is equal to 1 over 2. It is given that it is the desire to have the sideband power of the AM wave to be half of the carrier power. So this is equal to 1 over 2. On simplifying this, we will get AC square would be cancelled out. B square by 2 will be B square upon A square. This would be equal to, this is 1 by 2, it would be 1 upon 4. So from here we can easily find the ratio of A upon B. So A upon B is equal to 2 here. So easily we can find our answer. The D option is our correct answer. So here is another problem. Consider a white Gaussian noise process N of T with two-sided power spectral density Sn of f is 0.5 watt per hertz as input to a filter with impulse response 0.5 e to the power minus t square by 2, resulting in output y of t. The power in y of t in watts is. So calculate the power in y of t, which is equal to integration from minus infinity to infinity. The power spectral density is Sn of f is multiplied with the magnitude of the impulse response. So this is h of f whole square and df. So here this is h of f, but we have h of t. So it is simple using Parseval's theorem. So Sn of f is given 0.5, and using Parseval's theorem we can write it as magnitude of h of t whole square dt, and this term we can write it as 0.5 into 0.5 e to the power minus t square by 2 magnitude of this whole square dt. So on simplifying we will get 0.5 into 0.25 integration of minus infinity to infinity, it would be e to the power minus t square dt. So here we'll have to solve this integration. So consider this is I. So here separately I will solve this integration. I is equal to minus infinity to infinity e to the power minus t square dt. Consider another I with different variable e to the power minus s square ds. Now multiply this both the equations. So it would be I square is equal to minus infinity to infinity e to the power minus t square plus s square dt ds. So here you will see that this point is ts, and this is the diagonal square root of t square plus s square. Here is another integration would be there. So now you will see that this will cover the entire area if we integrate from minus infinity to infinity. Now we will put t square plus s square as r square. We'll convert, simply converting from Cartesian form to polar form. So here our I square would be 0 to 2 pi, 0 to infinity e to the power minus r square into r dr d theta. So here you will see that if there is an angle theta from 0 to 2 pi, right, and the radius r, a circle radius, is from 0 to infinity. This will also cover the full area. Now we will simplify this. So we'll calculate, we'll perform the integration with respect to r here. So it would be 0 to 2 pi, and this would be first e to the power minus r square, then it would be minus 1 upon 2 r, which is multiplied by r, and the range will vary from 0 to infinity d theta. Further simplifying this, so it would be 0 to 2 pi. This e to the power minus theta would be 0, and e to the power 0 would be 1. So minus of minus 1 upon 2, it would be 1 over 2. R and R would be cancelled out. So here we will get 1 upon 2 d theta. Further integrating, so here we will get 1 over 2 into 2 pi minus 0. So here we will get 2 pi only. So this is pi. So it is here, and that pi is equal to I square. So I is equal to the square root of pi. So here we'll put the value of I here, 0.5 into 0.25 into the square root of pi. So on solving this, we'll get approximate 0.22. So here our correct option is B, 0.22. Here is the next question. A random variable x takes values minus 0.5 and 0.5 with probabilities 1 by 4 and 3 by 4 respectively. The noisy observation of x is y is equal to x plus z, where z has uniform probability density over the interval minus 1 to 1. X and z are independent if the map, that is maximum a priori rule based detector, outputs escape as. So escape is given minus 0.5 when y is less than alpha and 0.5 when y is greater than or equal to alpha. Then the value of alpha is. So here it is given that the probability for x is equal to minus 0.5 is given 1 by 4, and the probability when x is equal to 0.5 is given 3 by 4. Another thing is given that z has the uniform probability density. Means that if you draw the PDF for this function, so it would be look like this. It is in the interval minus 1 to 1, and uniformly means the area under this curve is unity, that is 1. If it is 1, then its amplitude would be 1 over 2. So here this is the PDF of Z over Z. So now according to MAP criteria, maximum a priori probability criteria, the PDF of received symbol y at received symbol y and given x naught multiply with the probability of x naught should be greater than to the PDF of received symbol vector y at received vector y of at given uh, transmit symbol vector x1 and the probability multiply with the probability of x1. If this LHS is greater than this RHS, then we will choose uh, transmit symbol vector x0, otherwise we will choose x1. So this is the map criteria. Now here probability is given of x0 and x1 and we have to find the PDF of this. For this y is equal to x plus z is given where x and z both are independent. So easily we can draw the PDF for received symbol vector, which will look like this. So here is the PDF of received symbol vector. At first at transmit value at 0.5, we draw the PDF of y for received vector y given x0 at minus 0.5. So here it is simply in additive nature. So z is varied from minus 1 to 1. The distance of this is 2. So here it will also vary from this is minus 1 minus 1.5 to 0.5. This is 0, this is 1.0 and 1.5. So here it will vary from 0 to minus 1.5 to 0.5. This is the PDF of received symbol vector y and given x0. And we can also draw the PDF of this y of y given x1 at 0.5. It will vary from minus 0.5 to 1.5. So this is the PDF of received symbol vector y given x1. Here both PDF have the amplitude of 1 over 2. So here we will put the values of this. So this is 1 upon 2 into probability of x0 is 1 by 4. And this PDF is also 1 over 2 into 3 by 4. So this is x0 and this is x1. Here it is seen that 3 by 8 is greater than 1 by 8. Means we will choose the transmit symbol vector x1. And we will observe that the PDF of received symbol vector y given x1 starts from minus 0.5. So this point is going to be our threshold value. So here our estimator x cap is minus 0.5 when y is less than alpha, that is minus 0.5, then we'll choose the estimator minus 0.5, and it is 0.5 when our received small vector is greater than or equal to minus 0.5. So here the value of alpha is going to be minus 0.5. Next question is, a band limited low pass signal x of t of bandwidth 5 kHz is sampled at a sampling rate fs. The signal x of t is reconstructed using the reconstruction filter h of f whose magnitude response is shown below. The minimum sampling rate fs for perfect reconstruction of x of t is, according to sampling theorem we know that the fs should be greater than or equal to 2fm, but here the filter magnitude response is given of the filter. So we'll check for the perfect reconstruction of x of t. According to sampling theorem, there should not be overlapping between adjacent symbols. So here I will draw our band limited low pass signal in this figure here for better understanding. So it has the bandwidth of 5 kHz. So here it will varies from minus 5 to plus 5, and I will draw the adjacent symbol vector at the sampling frequency of fs. So here the upper frequency would be fs plus 5 and low frequency would be fs minus 5. So to avoid the overlapping between adjacent symbol, And for perfect reconstruction with this filter, this fs minus 5 should be greater than or equal to the upper cutoff frequency is given here, which is 8. So here fs minus 5 should be greater than or equal to 8. So from here fs we can easily found, which is 13. So in the question it is asking the minimum sampling rate. So minimum sampling rate is 13 kilohertz. So here we will write 13 in the answer. So that's all about for this video. We have completed the communications topic questions came in your GATE 2018 exam. So in the last, thanks for your kind attention. Your all suggestions are most welcome. Please like, share and comment and subscribe my channel. Praveen 25488. All the best friends. Thank you very much.